Very well. Good morning and welcome back after the midterm. I am going today to continue the conversation on mathematical optimization. Last time we did a broad overview of how you might solve large-scale optimization problems using software tools, et cetera, et cetera. Today, what we're going to do is to actually take a look at an illustrative example. This is actually a relatively simple example, not particularly realistic, with very few numbers, so that we can actually look at it and find the solution, in which I will try to build step by step all the elements that are important in an optimization problem. So we're going to make up a super simplified vehicle powertrain optimization problem in which we're going to have some performance objectives. There are three things that we care about. One is fuel economy. Let's say that we would like to achieve 30 miles per gallon. And imagine that this is just a conventional automobile for the time being. We want to have an acceleration time from 0 to 60 miles per hour of 12 seconds. And the top speed is going to be 180 kilometers per hour. That's about, those are the objectives, the goals that we would like to set. We don't know upfront whether it's possible to achieve all of these things simultaneously. So what data do we have? What information do we have? Suddenly my pen is not writing. Let's try again. Okay, it's not writing in blue. Let's try green. Green works. So we have some fuel economy data. We're assuming that we have constant vehicle weight, and what we've done somehow we've done some experiments where we've changed the engine size, and given the fixed vehicle constant weight, yes, the engine larger weighs a little bit more than a smaller engine, but it's not a huge difference. Then we've also measured the acceleration time, again, for constant vehicle weight and the top speed. So I have some data that tells me that for a vehicle mass of 1,170 kilograms, I have 6 different engine sizes that go from 50 to 175 kilowatts. And for those, I can see that I have fuel economy that goes from 20 to 29 miles per gallon. Then I know that for each of these different power ratings, I can get acceleration times from 0 to 60 that range from 19 to 6 seconds. And similarly, I have some data points in which, again, for each power rating, I know that the maximum velocity will go anywhere from 140 to 209 miles per hour. So clearly, I have trade-offs. I can't immediately visually see what the optimal configuration is going to be. And there may not be, remember that the goals I have set are targets. They're not guaranteed, right? There's no guarantee that I will be able. By the way, I put in an extra data point here, which says that if I have 0 power, then my top speed is probably going to be 0 miles per hour. Why not? I have an additional data point that I can use. So what could we optimize? We're going to go through all the different steps in a very simple way. I could do the fuel economy only, find the maximum miles per gallon I can get. I could optimize with respect to performance. I could do 2 things, have performance and fuel economy, in which I consider one primary and the other one secondary, or I could do the opposite and say, let the fuel economy be primary and the performance be the secondary objective. So what would I have to do? Well, let's think about it in a step-by-step version. The first thing I have to do is to define a cost function. And so to define a cost function, I need to be able to manipulate things mathematically. And so why not convert this numerical data in a mathematical function? So what you will see is that we're going to try to do some curve fitting of some kind. Second step, now I have to build an objective function. Now, we will begin by building an objective function that is a weighted sum of elements, because remember, there were different things that I was interested in optimizing. Finally, I could then say that I can impose some constraints. We'll see what effect that has on my cost function, and include some kind of a penalty function. Okay. Now, why are we doing this? So there is an important observation here. So oftentimes, if you go into the experimental data that might be available in an automotive company, you might come up, they'll give you some Excel spreadsheet where you have tables of measurements done, for example, in an engine test cell, fuel economy versus engine power, something like that. And the fact, though, is that if you want to use formal mathematical optimization techniques, we would like to have a functional form. So we'll spend a little bit of time thinking about how we could fit the data so that we can get an analytical expression. Now, the objective function, of course, is very important. It depends on the variables for which we're performing the optimization. And we would like the objective function to reflect the relative importance of the different criteria that we're wishing to optimize. So, as I said, first job, convert the numerical data into a mathematical function. Let's go to curve fitting. Okay, this is a perfectly reasonable approach. So what you would like to do is obtain a best description of the data you have in the form of a mathematical function. Obviously, there isn't a single answer. That's pretty clear. And first, you're going to have to choose a functional form. We try to think of functional forms in a simple way. I don't expect that most of you know what a Volterra series is, but if you've heard about it before, it's a very complicated mathematical representation. If I have a bunch of data points in a map, I probably will not start with a Volterra series. Maybe I'll start with a polynomial approximation, right? I also have to pay attention to how noisy and sensitive the data is. Once I have done that and I have somehow curve fit, well, once I have curve fit the data, interpolation between data points is not such a bad thing to do. It's perfectly reasonable. Anything that falls within the span of your data is reasonable. But very poor for extrapolation. We don't want to really take a curve fit as an opportunity to extrapolate, because extrapolation means that you go outside the data you know, and so how do you know whether that's true or not? Second point, one might be tempted, especially today in the days of powerful MATLAB functions, to throw the data into the mill, turn the crank, and out comes a function. Well, it's really a good idea to think about the physics of the problem to make sure that the function that you use for, it's fascinating, my pen sometimes works, sometimes does not. Why? There you go. We're interested in the physics of the problem. We want to take that into account, and I'll show you some example of that. So would it make sense to say that something is linear? It's possible, right? So if physically you say, yeah, this is proportional to that, use a linear function. Sometimes a power law, y is equal to x squared or x cubed or something like that, might make sense. Some things might be fit well by an exponential. Usually the physics will give us some information related to that. One of the important elements here is overfitting, okay? And I'm going to show you an example. This is bordering on a stupid example, but if you haven't thought about what overfitting means, it's good to look at this. So let's imagine now that I just collected some data, and it looks something like this. Okay. I'll give you two extremes. I could look at it and say, okay, that looks linear. Let me do a least squares, and that's the best fit line. Okay. Or I could say, I'm going to close my eyes and trust MATLAB to give me an answer, okay? And so I go into some kind of a complicated optimization toolbox, pick some function, and what MATLAB tells me, it does a perfect fit where the error is absolutely zero, but it gives me a 15th order polynomial. Okay. Now, what's going to happen if you do that? You come back to me and say, I'm so happy. I had 16 data points and I fit it perfectly with a 15th order polynomial. Yes, you will do exactly that. It works exactly that way. But now I give you another data point, or two data points, which actually are still in the neighborhood, and all of a sudden your model doesn't work anymore. So the idea of overfitting is that you really have to think carefully about how many data points you have and how complex a function fit you want to make. Simpler is always better. Okay. Now, to force something to be a straight line where it isn't a straight line because there is some curvature is not a good idea. So you really do have to think a little bit about the shape of things. But overfitting is a very common problem that should be avoided. One sometimes is tempted to say, oh, I'll increase the order of my model because I'll get a better fit. Well, you get a better fit for that specific data set, but you typically are modeling something that is much larger than that. In the end, how do you decide how well your fit works? Well, think about two things. One is there is an error function, the error between the data points and your curve fit. That's one criterion. But really looking at it, a visual evaluation oftentimes ends up being the most useful thing. So let's take the data we have and do some fitting. So fuel economy versus power. Okay, so this is MPG on the vertical axis and power. The green points are the data points that we have. In blue, you can see a fit that you look at it and you say, yep, that looks pretty good. I could believe that. It looks like it sort of follows that trend very nicely. How did I obtain that? Well, there isn't really any immediately obvious relationship between fuel economy and power. The only thing that is clear is that probably the higher the power rating of the engine, the lower the fuel economy. And that, in fact, is exactly what this curve shows. But is that a linear relationship? Is it some other kind of relationship? There isn't anything in the physics. This is a complicated problem. Engines are not simple, okay? So what we did in this case, and this was kind of an eyeball estimation, you just look at it and say, let me try a quadratic. Why? Well, it has some curvature, could be a quadratic function. It's not linear. A quadratic function is the simplest thing that I can do other than linear. And so there you have it. So this is a function that looks like this. Miles per gallon is equal to a constant, A0, plus another constant, A1 times power, plus another constant, A2 times power squared. It works well enough, so I could stop here. I don't really need to go much further than that. Could you have used another function? I mean, if I challenged you to come up with a different way of representing the same information, sure, you could have come up with other functions that would do that. But quadratic is about as simple as it gets. 0 to 60, acceleration time versus power. Okay, now, when I think about this, the first thing that comes to my mind is F equals ma, right? F, of course, and A, they're related to one another. Force and power are related to one another. It seems to me that I could fairly easily do by just reasoning physically, I could fairly reasonably propose that the time it takes to accelerate from 0 to 60 would be inversely proportional to power. In other words, the more power I have, the shorter the time. So this 1 over x relationships works pretty well. So I have a number of data points here, and here is my curve fit in which I fit it to a function in which I have, again, a coefficient A0 and a coefficient A1 divided by P. Okay. If you look at the curve fit, that makes pretty good sense. Okay. In fact, that's a really good fit. And the fact that acceleration time would be inversely proportional to power is satisfying. Okay. What about top speed? Here's where you go back and think about some lecture way back when we talked about road load, okay? What happens to top speed? Well, the power is proportional to velocity. It's force times velocity. But what's the aerodynamic drag force? That's proportional to the square of the velocity. So the drag force, aero drag force, is proportional to the square, but power is proportional to velocity itself. So you're going to have some kind of a V cubed relationship. Okay? Physics again. So the top speed of my vehicle, eventually, when I get to the top speed, aerodynamics is going to be my ultimate limit. So how about if I do something in which I say Vmax is proportional to the cube root of P. And sure enough, if I come up with a model in which I take a coefficient, A0, a constant, that's a bias, and then I'm going to have some coefficient, let me call it A3, which is proportional to the cube root of power in kilowatts. And there you go. You can see that this works quite well. By the way, I also added an extra point. This is important. Okay. Because if you only had the data points given, you might be tempted to say that you have something that could be modeled by a straight line or by a quadratic. Why? Because the smallest data point we have is for 50 kilowatts. So what we did in this case, and you remember I pointed this out in the beginning, I actually threw in an additional data point because we know that a physically meaningful curve here has to go through zero. Because my top speed, if my engine has zero power, is exactly zero. I mean, unless I'm going downhill, I suppose. We're assuming a flat road. Okay. So there you have it. When you throw in this last data point, the 0, 0 data point, that's where you're going to get a power law or cubic root relationship. It's very important to do this because you might otherwise be tempted to think that power and top speed are related linearly, but that's not true. And that's, I just said all of this about the 0, 0 data point. Now, you could also do a technique that is called weighted least squares. So least squares is a method that gives equal value, equal weighting to each of the data points that you have. But you might say, look, there is a data point that is very important to me. I want to make sure that I fit that data point exactly. For example, 0, 0. So I might give some weighting to that data point so that my curve will have to go through 0, 0. Then it can approximate the other data points. So there are some notes on least squares. Claudia, could you check and make sure that that is true, that that is actually on Carmen? But there should be some notes on least squares because this is not, I'm not going to lecture on the least squares per se, okay? What you find is that least squares solutions are essentially a matrix problem in which you have to solve a matrix equation, and in order for a least squares problem to be solved well, the matrices need to be well conditioned. So there are some notes on some subtleties that have to do with solving least squares problem. Now, conditioning of the X matrix, which is the data that you have, is very important, or it is very dependent on the scale. So let's imagine that I choose some really strange units in which my top speed is expressed in furlongs per fortnight. Does anyone know what a furlong is? Some of you must. Furlong is 1/8 of a mile, and a fortnight is 2 weeks. Okay, so if I were to use units of furlongs per fortnight for my velocity, I would have some really large number corresponding to 80 miles per hour, okay? And then on the other scale, I could say that time is measured in nanoseconds, for example. you could have a matrix that is incredibly ill-conditioned if you do this, just for numerical reasons. So what you want to do is rescale the data. So for example, one way of rescaling it would be to say, what do I expect my top speed to be? 85 miles per hour. Let me divide my velocity data points by 85 miles per hour so that the maximum value is going to be 1, and the minimum value, of course, is always going to be 0. Then I will take other variables that I have, engine power, for example, divide everything by the maximum power, so again, I have numbers between 0 and 1. This, when you are scaling things so that each variable ends up being represented in the range 0 to 1, you are reducing to a minimum the problem of numerical ill-conditioning caused by improper scaling. Of course, at the end, when you're finished, you're going to have to unscale the variables, but that's the easy part. So, we did step 1. We talked about taking the data and representing it by mathematical functions. And we came up, what did we have? We had a quadratic relationship. We had a relationship that was a cubic root, and we had another relationship that was, I forget what it was. Huh? An inverse, yeah, a hyperbolic function, right, exactly. So these are all things that we understand, we can put in a computer. Yeah, the hyperbolic function is a little difficult, don't make the denominator equal to 0, okay, but in that case it wasn't going to happen. So now what we have to do is, the next step is we have to build an objective function. So we normalize all the variables to make them between 0 and 1. And let's think about it for a moment. How do we normalize? Well, we have fuel economy, mileage in miles per gallon, 0 to 60 acceleration time, and top speed. So that's why it was important in the beginning to select some parameter values that we were interested in. So 30 miles per gallon, 12 seconds, 180 kilometers per hour. Those are just targets. It doesn't mean that we will necessarily meet them, but these are good normalization factors. Okay? So we could construct an objective function. So let's make it. Let's say that we're building an objective function, f, in which we're going to have a normalized version of the miles per gallon value, normalized by some target, 30. We are going to have an element of it that is going to be the time from 0 to 60, and that's again normalized to some standard value that we have selected, for example, a target of 12 seconds. And then we're going to have a maximum velocity of the vehicle, again normalized. And now for this, we're going to have coefficients alpha, beta, and gamma. So what are the properties of these weights? Well, clearly they're positive numbers, and their sum must be equal to 1. Pretty straightforward. Because we have normalized every variable but by some standard reference value, this is a non-dimensional equation. Everything is approximately in the range 0 to 1, and it's dimensionless. So what we want to do, we want to minimize f. Why do we want to minimize f? Because f is going to decrease as the mileage increases, as the top speed increases, and as the 0 to 60 acceleration time decreases. That's one way of constructing the function. Could you think of another way of constructing this function? I am sure. In fact, there is an infinite number of ways in which we could build some kind of a cost function, but this one, in which we're adding the different objective functions and giving each of them a weight, is a simple thing to do, and not only is it simple to do, but it lends itself pretty well to interpretation. For example, what does it mean if my value of f, when I am done optimizing, is less than 1? If it's f is less than 1, it means that collectively I have exceeded the objectives that I set. This is even better, because remember I had some target values. The denominators that I used to normalize are target values. So if I get an f that is less than 1 at the end of my optimization, I have exceeded my target values. On the other hand, an f greater than 1 will mean that I'm not quite there. So let's do some simple things. These are really intuitive things. Let's imagine that I want to minimize f, and I want to only consider fuel economy. Miles per gallon is the only thing I optimize. So it's pretty easy, because I'll pick beta and gamma equal to 0. I don't care what the top speed is. I don't care what the acceleration is. If I do that, and I construct my f, what I'm going to find, so these two terms are not in the picture. I construct my f. What I'm going to find is that for a very large value of power, my fuel economy won't be as good. Larger engines are not as fuel economical. As I move down, I have a monotonically decreasing function such that my smallest engine, 50 kilowatts, is the one that is going to have the lowest fuel consumption. Did I know that before starting? Yeah, we knew that. I mean, it was pretty obvious. We haven't said anything about whether this vehicle is drivable on the public roads. It's probably completely unsafe, right? But you could do that. Okay. So lowest number is the value. By the way, let me also make the point that notice that the final value of my function is a little greater than 1, meaning that I haven't quite succeeded in obtaining what I wanted. If you go back and take a look at the numbers that we used, remember that that smallest engine gave me a fuel economy of something like 28 or 29 miles per gallon, something like that. So in fact, the data I had to begin with does not support my desire to have 30 miles per gallon as a target fuel economy. I can use that as a target, but I will never reach it, because even the smallest engine is not giving me 30 miles per gallon. Now, at this point, you could say, oh, maybe 30 is not a good target. Maybe I should go to a number like 25 so I can achieve it. But in a sense, it doesn't matter. Everything is relative. You're looking for the best. You're not looking for a specific number. Okay. So that's what this means. The minimum value is greater than 1. We are not quite capable of meeting our target. Okay. Now, there is another solution. Again, you close your eyes, extrapolate, let MATLAB give you the answer, and the answer is going to be, oh, I can have 0 fuel consumption if I take the engine out of the car. Okay. Well, mathematically, that is the minimum. But practically, obviously, that's not a practical vehicle. You may have installed some pedals, you know, and see if you can bicycle your way around with the car. So again, this is a silly example, but it points out that you really want to think physically at all times. So now let's take a second option, and we're going to now optimize for performance only, okay? And this time what I'm going to do is select alpha equals 0 and beta and gamma equals 2.5. I want to have a compromise between my ability to accelerate and my ability to arrive at a top speed. Realistically, I'm probably, whether it's 0 to 60 acceleration time or top speed, obviously those are answers that favor a larger engine. And so in fact, if I begin right here with the 50 kilowatt engine, my value of the function is 1.5 or close to it. As I keep increasing the engine power, I eventually come up with a minimum that is, of course, the largest engine I could get. This is also a totally intuitive solution. And in this case, watch this. The value of f is 0.6. In other words, I'm doing a lot better. So in my original targets, which were arbitrary, selecting 180 kilowatts as the largest possible engine was overkill. Whereas selecting 30 miles per gallon as a target in the objective function was not something that could be achieved. So here you have two different cases in which my performance objective, 0 to 60 of 12 seconds, and top speed of whatever we said, 180 kilometers an hour, those were eminently achievable with the powertrains I had available, okay? And that's demonstrated by the fact that I have 0.6 here. So again, this time, the best solution exceeds the performance target. We should be able to do a lot better than 12 seconds and 180 kilometers per hour. Now, what would have happened if instead of 0.5 and 0.5, I had selected 0.4 and 0.6? Do you think the answer would look different? Well, sure, it would look a little different. It might fall down like this or like that, but in the end, the answer would have been the same, which is that the minimum would be at the extremal point of 180 kilowatts. Okay. So you can clearly see that this is a reasonable answer. So now let's do something that is a little bit more interesting. It's clear that if all I want is fuel economy, I'll pick the smallest engine I can. If all I want is performance, I pick the largest engine I can. Well, gee, surprise, didn't you know that already? Sure. So now let's see where we go if we try to select coefficient values that are equal weighting. Actually, this is not truly equal weighting because two of my criteria are related to performance and one is related to fuel economy. So in fact, I am giving 2/3 of the weight to performance. So in this case, what I'm going to say is that performance is my primary goal. By the way, by now, you might be thinking, gee, do I really need to separate acceleration from top speed? It seems that both of them want a larger engine. Maybe I don't need 3 criteria and 2 would be good enough. It's possible. Yeah. So now things become interesting because you are considering each of the 3 elements, okay? And when you begin with the 50 kilowatt engine, you are going to obviously not meet the criteria because performance is not acceptable. And you're going to reach some point where you're close to achieving as a target. Remember that our target is something like around 1, okay? You begin to come close to your original desire at 100 kilowatts, okay, where you're going to have the desired compromise between fuel economy and performance. But if you keep increasing the engine, your cost function as defined is going to continue decreasing because more power will give you lower acceleration time and higher top speed. So because of the way you built the cost function, if you keep increasing the engine power, you will lose on the fuel economy, but you're clearly going to gain on the performance. And you're giving 2/3 of the weight to the performance. So it turns out actually that your minimum is going to fall, give or take, around 140 kilowatts, because what happens now, if you keep increasing the engine power, you will lose more and more on fuel economy to the point now that it's going to offset the benefits that you have. Okay. So in this case, your minimum would numerically would end up to be something around 140 kilowatts. So if you want a vehicle that has pretty solid performance and does okay in fuel economy, there you have it. That's a good choice of engine. So we also make the point that this minimum is around 0.95. So we have exceeded our requirements, okay, in building the cost function. Okay. And it's also important to notice that this is not a sharp minimum. It's kind of a continuum, okay, that is relatively shallow. It's relatively flat around the minimum. So in a sense, it doesn't matter too much. We'll talk about sensitivity later, but basically our solution here is not that sensitive to the size of the engine. You could probably make the argument that anything between 120 and 160 kilowatts would give you comparable solutions. Okay. So now let's do things differently. And let's say, no, I have to meet CAFE regulations, life is tough, I can't be having a vehicle that has that fuel economy, I need to do better than that. So I'm going to now choose alpha, the fuel economy weight to be 0.8, and beta and gamma I'll put in 0.1. In other words, I am really de-emphasizing the performance. Well, you already understand what this is going to look like, because now I still have the same type of behavior. I begin, the smallest engine doesn't quite do it. I keep decreasing. I find the minimum. It tells me that a little over 80 kilowatts is the minimum. And then as I increase the engine size, I go away from my minimum because fuel economy has a very strong penalty on it. We also observe that when you look at this result, your minimum is greater than 1. In other words, if you put so much weight on fuel economy and too little weight on performance, you're just not going to meet, you're not going to come close enough to meeting or exceeding your objective. And what this illustrates, philosophically, the point is very simple. You can obtain any answer you want by selecting alpha, beta, and gamma. Okay, so if your chief engineer comes to you and says, you know, all I have is 120 kilowatt engines today, you can find the value of alpha, beta, and gamma such that your answer becomes the one that makes your chief engineer happy. Okay, so the point about this is that this weighted sum of costs in a cost function is helpful in guiding your decisions, but you really do not have a unique answer. The real question is, how do you choose the weights? And in this case, for example, if I had selected 0.6, 0.2, and 0.2, what do you think might have happened? You probably, the shape of the function would have been similar, but it might have looked more like this. Okay, in other words, I clearly would have selected a larger engine and probably would have come closer to an F equal to 1, probably. Okay. So this other observation, this is maybe qualitative, but maybe the minimum, the function is less flat around the minimum. It's a little bit sharper for those values of coefficients. So the idea, again, I think I've already made the key point, is that you can obtain any answer you want. So when you solve an optimization problem and you choose the form of the cost function and the weighting of the different elements of the cost function, you have to think about what that means. You can't just say, oh, let me just make them 1/3, 1/3, 1/3, because by doing that, you have already made some a priori decision. So there is another observation that is important. This was an unconstrained problem. We didn't place any constraints on it. We just simply said, we have this data, we'll operate within the range of solutions that are made possible by the numbers I have, but I'm not going to impose specific constraints. Let's see where the mathematics takes me. Another way of doing the problem is to set some constraints. In fact, we had already some implicit constraints in the previous problems, okay? Because the implicit constraints already existed by saying the smallest engine is 50 kilowatts, the largest engine is 180 kilowatts. But I could also impose constraints in the objective function by, let me give you a simple example. Let me say, I shall not have any 0 to 60 time that is greater than 13 seconds or something like that. So instead of making the 0 to 60 acceleration time one of the elements of the cost function around which you optimize, you could actually impose it as a constraint and say, I'm not trying to minimize the 0 to 60 time. I just want to be sure that it doesn't violate some limit that I'm going to pose, which is a way of saying I want the vehicle that is going to have the best fuel economy, but it must accelerate at least as fast. Okay. So you could do you could now redesign the function f to include constraints, and you could penalize the function, including constraints. And so a penalization would be that you could basically represent it as a discontinuity. Anything that is less than a certain amount is acceptable. Anything that is more than a certain amount is not acceptable. Well, this would be a discontinuity. And as we go forward, we're going to move ahead. You'll see in Friday's lecture, we're going to use mathematical techniques in which we will essentially use the good old concept of, to find the minimum of a function, you calculate the derivative of the function with respect to x and set it equal to 0, right? Well, in a larger scale problem, when you have multiple variables, we don't talk about derivatives, we talk about gradients. But gradients are generalized derivatives, and basically, if you have a discontinuity, that's a problem. So what could you do to impose constraints in such a way? And remember, we talked about this constraint when we talked about ECMS. We said, hey, I want to make sure that my state of charge stays around some target value. If it deviates too much in one direction or another, I want to penalize that. Okay. That's ECMS. So we're solving an optimization problem. And we had selected a cubic function for that one. We normalized state of charge around 1, and then we created a cubic function that... So, in fact, even better than that, I could select a function that has a very pretty sharp but continuous behavior. So something that approximates a step change. Anything less than this value will not do, anything greater is acceptable, for example. But instead of doing it with a discontinuous function, I could, for example, select a hyperbolic tangent. Okay, you know what those things look like. We'll take a look at it in a moment. And so what you do then is the inflection point of this curve is going to be located at the value of the constraint. Okay. And as you move away from that constraint in one direction, things are good. In the other direction, things become very rapidly quite bad. And it's differentiable, so you can do it. So here is a plot of a hyperbolic tangent in which I have the element alpha here, the parameter alpha, changing from 1 to 2 to 10. Now this looks piecewise because the function was implemented in MATLAB with just a few data points, but in fact the function itself is continuous. Okay. So this is also called an interior penalty function because it rises inside the feasible domain. Notice this. What have we done here? We have accepted the fact that I have values of 0 to 60 acceleration time in the data that is available to me of 6 to 20 seconds. Those are all possible. But I've selected a target that is 12 seconds. So I will put that right in the middle. That's the point of inflection of my hyperbolic tangent. And what's going to happen now is that values that are near 12 seconds are they're not going to see a big penalty, but values that begin to deviate significantly from my 12 seconds in one direction or the other are going to see a higher penalty. So if I now incorporate this penalty into my cost function that I had created. So I have this f, but now I add a penalty function to it. Okay? Then what will happen is that in my minimization is going to change dramatically. So what I'm going to do is scenario 4. Remember, scenario 4 was not very good for us, right? Because we had given very little weight to the performance criteria, okay? The answer intuitively, physically, we didn't like very much because by having given those small weights to acceleration and top speed, we had overly emphasized the engine size. Well, how about if we now put a constraint on it and say, yeah, we're going to have a penalty if T60 is significantly greater than 12 seconds. So you can see here that my penalty increases quite rapidly as I have acceleration times that are greater than 12 seconds. So what's going to happen is because of that penalty, this area here, which in the unconstrained optimization was somewhere, look something like this, now we have pushed it way up there. And what's going to happen now, let's go compare. This is telling me basically that I need maybe a 95 kilowatt engine to do that solution, because I'm going to penalize any solution in which the time from 0 to 60 is much greater than 12 seconds. When I look at the previous answer, what did we have? We had a little over 80 kilowatts because I didn't have that constraint. And so I accepted solutions that gave me not very attractive times from 0 to 60. So we took that curve, and by putting a penalty in it, we ended up with a very different shape here on the low end. Okay. So you can see that incorporating a constraint is a reasonable thing to do. I could do something similar for the second constraint, and I could also say, look, again, if my Vmax deviates significantly from 180 kilometers per hour, so now I can do another hyperbolic tangent in which my inflection point is at 180 kilometers per hour, and now I put two constraints on my optimization. One that forces the times from 0 to 60 to not exceed 12 seconds by much, because you pay a penalty, and one that forces the top speed to not be much lower than 180, otherwise you incur a significant penalty. That same optimization now is going to change, and I am going to further expand. Let me do it in red. I'm going to further expand the region. Before, things might have looked something like that, okay? And so with that additional penalty, I am moving things further to the right, and now my optimum is going to be around 110 kilowatts. So by imposing these constraints, I have moved from an answer that probably was going to be unsatisfactory in terms of vehicle performance. I have moved it from 80 to 90 to 195 to 110 kilowatts. Now, these are very simple-minded illustrative examples, because you could tell me, oh, well, why did you choose 0.8, 0.1, 0.1? If I had selected 0.6, 0.2, 0.2, I could have also come up with the same answer of 110 kilowatts. So the point here is not specifically to solve a problem. The point that is more important here is to illustrate the fact that you can attack the same problem from different angles, one of which is simply a weighted cost function with different elements. Another one, on the other hand, could be to impose some constraints. Notice that in this case, I have imposed the constraints after having created the cost function. You might then say, wait, is it possible? Could I, instead of having a cost function that has weighted fuel economy, acceleration, and top speed, could I just simply minimize fuel economies but impose the constraints on top speed and acceleration? If you're thinking that way, you are thinking in the right direction. Why not? Why would you have to have a multi-objective cost function when you could deal with two of the objectives by saying, okay, let me just set some limits. I don't want to be any worse than this, so make it a constraint. And so you can do that. I think this is just an evolution of the same idea. I've already said all the things that I wanted to say, but I'll make a point. There is one more point in this plot, which is that when you finally have achieved your desired value, you are somewhere around 1.1. So in other words, you are not close to 1. And there is a fundamental structural problem in the way we pose the problem, because we said, hey, my fuel economy target was 30 miles per gallon, But frankly, none of the engines I gave you could meet 30 miles per gallon, so it actually was not a realistic target. So the fact that you don't get to one, per se, is not a problem. It had to do with the way you had set up the values in the beginning. So, and here you can see this is no constraint. And this is the first constraint here, and this is the second constraint there. So you can see that you're making increasingly restrictive as you add constraints. And the point I just made, you're not meeting target mileage. That actually was impossible. In fact, if you now, let's think about a case where I would not be able to solve the problem, period. If I now said, oh, let me find the solution in which I constrain the target mileage as well, just like I constrained the acceleration and top speed. And if I try to set the target mileage around 30, that's what I want to do. And if it's much higher than that, I have a penalty function. Is it possible that could I not find any feasible solution? Well, the answer is yes, in part because the problem was ill-posed to begin with. The 30 mile per gallon number is not a good choice, right? Because none of the engines could give you that anyways. So one of the things that you want to do is to make sure when you define a problem that you're not over-constraining it. Because if you start saying, I want the federal budget to be balanced, and I want free health care for everyone, and I want free college education, which raises the question for me, how do I get paid? Et cetera, et cetera, et cetera. You put all these constraints. Well, it's impossible. You can't do it. And no taxes. I forgot the other important one. 0 taxes for everyone. Well, of course, that's going to be a problem that is over-constrained and I cannot solve. So how do we balance these things? So what I had said earlier now was that this example was purposely generated to be a 1D optimization problem. What do I mean by a one-dimensional optimization problem? What I mean is that I am just simply trying to minimize a single variable, f, okay? And I wrote a weighted sum, I put in some constraints, but fundamentally, I was just minimizing just one f. You may now remember that when I gave you the example of that large-scale optimization study that we had done back in 1997, what we did on purpose in that problem was to not write a specific cost function, but to say, yep, time 0 to 60 is a cost. I want to minimize it. Top speed is a cost. I want to maximize it. Fuel economy is a cost. I want to minimize it. And then I started plotting them one against the other. I did not say f equals to a specific function of these things. I actually visually looked at trade-offs. I created these Pareto fronts, these curves that I could look at 2 variables at a time, or if I take 3 variables, it becomes a surface. If I have 4 variables, it becomes a hypersurface, et cetera, et cetera. Okay. So the idea is that here, lead problems, real problems are going to have multidimensional objectives. And at some point, it becomes difficult to visualize them, because if I now throw in a few more things, cost. So now I have fuel economy, acceleration, top speed, cost. What else could I throw in? Packaging space. Ooh, that's a really difficult one. How do you quantify that one? And I could go on with other things that are absolutely realistic. So I could throw cost, I could say initial purchase cost, but then I could have payback. Since I have better fuel economy, I will regain my initial purchase cost in so many years. That's called payback. Well, that's another criterion, right? And so now I'm already up to 6 cost criteria in my how can you visualize all 6 of them? Up to 3D, we can do it, but beyond 3D, it's a little difficult, okay? So the point is that you really need to think very carefully about how to solve multidimensional problems. And one way of dealing with multidimensional problems is going to be that constraints are actually going to allow you to reduce the dimension of the mathematical problem you solve. For example, let me say payback. I had 6 things, right? I'm going to say now my payback must be no more than 3 years. The purchase price of the vehicle must be no more than $35,000, okay? So instead of trying to optimize all these things, let me put some constraints in there where all the solutions that are going to be more expensive than $35,000 and that don't have a payback of 3 years or better, they're just not acceptable. I don't care how good the fuel economy is because it won't work economically. Well, I have just turned a 6-dimensional problem into a 4-dimensional problem. So that is another important thing to consider. Next, what are other things that happen when you have multidimensional problems? You know, in all the curves that I showed you here, how many minima of the function did you have? Well, somehow, magically, there always was just one minimum, okay? So we could happily say, yep, I found it. For these conditions, that's my minimum. We did not come up with a function that looked like this, okay? But the more complex the problem begins, the more you have to worry about the possibility that you might have local optima, okay? That is, if you're using a smaller engines in a smaller range, that's your best. If you're willing to use engines of a larger power size, your best is in a different place. Not only that, but oftentimes you have shapes like saddle points where you have surfaces, pick a 3-dimensional surface, you're going to have curious shapes that are going to give you perhaps a minimum with respect to some variable, but that's a maximum with respect to some other variables. So let's expand the problem that we just looked at in some simple way. So we purposely ignored mass in the first problem. Regardless of how we changed the powertrain size from 50 kilowatts to 150 kilowatts, I forget what the number was, 175, we had a constant vehicle mass. Is that true? No, it's not, because a 4-cylinder engine has less mass than a 6-cylinder engine, which has less mass than an 8-cylinder engine. Does mass affect some of these variables? Sure it does. Fuel economy without any question. But how about acceleration as well? So you do have more power with a larger engine, but you also need to accelerate more mass. So that is something that you should include. And so power and mass are going to be related to one another. So you could say, oh, in my cost function, I also need to now take into account of some kind of a term that incorporates the relationship between power and mass, because there is probably some function in which the engine power is a function of mass. There is a correlation between the two. Maybe it's linear, okay? So you could have some cross terms in your cost function. What about the transmission? Okay, we forgot something. I mean, you didn't forget because you paid so much attention during each of my lectures on transmissions and on vehicle road load, right? You remember everything. You remember that the selection of a final drive ratio and of the individual gear ratios has a huge effect on the acceleration of a vehicle. So you could say, wait a minute, you can't just give me engine power. Tell me something about the transmission and the final drive ratio. If I don't know those things, how can I tell you what the acceleration and top speed are going to be? I could find really short gears that give me fantastic acceleration, but then my top speed is limited to 65. So I have to put in gear ratios in there as well. And so as you go on, you can see that the problem becomes more and more interesting and more complex. Next, let's say that we have arrived at a compromise. We are a team, and we have come up with some optimization problem that includes a cost function, maybe multidimensional. We have some constraints. We've implemented everything. We find an answer. We turn it back, we go to the chief engineer, okay, and we say, hey, chief engineer, here is our answer. This is how I think we should design the next vehicle. And the chief engineer says, wait a minute, the aerodynamic design group is still working, okay, and so you made your power versus top speed relationship will be dependent on finally whether they decide to put in a fender that has very low air drag but is more expensive, or an old-fashioned fender that gives you a little bit more air drag but is cheaper. We haven't decided that yet. And so now you're going to have to think about sensitivity. Your answer, in which you had assumed that the relationship between top speed and engine power was proportional to V cubed. Remember, we had we looked like my power was something like A0 plus A1P plus A2P squared plus, plus A3P cubed. That was not power, the first version. It was Vmax, right? My maximum velocity is going to be proportional to the cube of the power, something like that, okay? We had selected coefficients A0 to A3 based on what? On some data that had been collected on vehicles with different powers. But that was for a fixed aerodynamic configuration, right? The vehicle, it was a prototype that I took to the proving ground and did some tests on. Now my chief engineer is telling me that, by golly, the aerodynamics of a prototype are not necessarily the final aerodynamics. My CDA, my drag coefficient times frontal area, CDAF, could be in a range between some maximum and some minimum value, which means that my coefficients here will change. Okay. So how do I deal with this? Now I'm going to have to evaluate the sensitivity. I am going to have to understand, if I don't have a single curve of Vmax versus power, but a range of Vmax versus power. So let me sketch what this might look like. I have Vmax as a function of engine power, right? And I had some data points that look something like this, okay? In fact, what's going to happen is that I am probably going to have a range, okay, because I could have better or worse aerodynamics, right? So if I'm operating in this range here, how sensitive is my answer, my cost function, with respect to that particular criterion? So remember, I had a curve fit that I had made of this function, but now that curve fit is only true for one particular vehicle design, but I don't know which vehicle design I'm going to have. The aerodynamics will change. So the idea is that evaluating the sensitivity of the objective function to a specific uncertainty in some parameters of your problem, some characteristics of your problem, is very important. Second, there is another sensitivity that is very important, that we cannot ignore. And that's the sensitivity. So let's say that we had our criteria, we had alpha, beta, gamma. Let's call them alpha 1, alpha 2, alpha 3 for simplicity. Okay. You might also ask yourself the question, how sensitive is my optimum and my answer, therefore, to changes in those weights? Okay. Is it possible that as I move the weight alpha 1 to alpha 1 plus epsilon, okay, with epsilon small, that my solution blows up and goes to a completely different place? That would be super high sensitivity. I would have to rethink the formulation of my problem if that were the case. So The sensitivity could be with respect to some physical parameter, to some of your data. Your curves are not representative of all possible conditions. You have uncertainty. Also, the optimum is sensitive to the values you selected for your. Remember also that we had a coefficient alpha in front of that hyperbolic tangent, right? How sensitive, you implemented a constraint, right? We implemented a constraint saying we'd like the 0 to 60 to be penalized if it's much larger than 12 seconds. Fine. I built a hyperbolic tangent. There was a tuning parameter in that hyperbolic tangent that I could give different values to, and I showed you 3 different curves, right? How sensitive is my answer as I tweak that parameter for my constraint? So it could be the actual coefficients of my weights. It could be something that I'm sensitive to. My constraint could be something that I'm sensitive to. So, conclusion of all this is that we have talked about a very simple-minded example that you can follow intuitively, and it's something for which the intuitive answer was already clear in your mind. You know that there is a trade-off between performance and fuel economy in a vehicle. What we did was to use a very simple example that you could easily duplicate. By the way, the numbers are in the lecture. If you wanted to play with this, you could. Okay, I'm not suggesting that you do that. The problem is too simple. We'll give you better things to work on, okay? But the idea is that you now have a concept of, when you solve an optimization problem, of what the challenges are. So what we're going to do on Friday will be to actually take a close look now at formulating these problems mathematically, using approaches that use gradients, and we will define certain special functions. One is called the Hessian, for example, that are going to allow you to formulate this problem mathematically in a more grown-up way than the simple example we did by hand today. When we're finished talking about what I'm calling now static optimization, because we're optimizing a static problem, there are no dynamics in it. Later, the last section of the course is going to now deal with how you solve a dynamic optimization problem or an optimal control problem, in which now there are states that vary dynamically. The underlying relationships are not just a bunch of curves that could be hyperbolic functions or quadratic functions. No, they're going to be differential equations. We're going to have x dot equals of f of xu, okay? And so if things change dynamically, how do you solve such an optimization problem? Question mark. And the answer is using a fundamental approach that is called optimal control. And you will see then when we get there that optimal control is a subject matter in and of itself, and we offer a high-level graduate course on that. But I can probably explain to you how to solve optimal control problems quite simply or in a straightforward way, and you will learn how to actually implement dynamic programming solutions, which is a numerical way of solving optimal control problems. So stay with me. We got a long way to go yet in the semester, but from now on, the words optimal optimization, optimal control are going to be the key to most of what we're doing. So have a great rest of the week, and I will see you here Friday morning to continue this discussion of mathematical optimization.